we're going to. Perfect. So we'll start with the limit comparison test. Once again, this one, we got two different series that we're looking at. So we need a sum or a series of a sub n and a series of b sub n. And both of those have to be positive. They all positive terms. And for some index of capital N, there's all positive after some n value. Right? Always positive after some n value. And so the limit comparison test said that if the limit as n approaches infinity of a sub n over b sub n is equal to any value, we'll call it c, where c is between 0 and infinity, then we know that a sub n and b sub n both converge or they both diverge. And so that's helpful because we can always just take some series that we know whether it converges or diverges and use this limit comparison test with the series that we're looking at. There's tons of series that we know the convergence or divergence of. And usually the way we do that is, if we end up with something like, I don't know, let's say we have the series, the sum from n equals 1 to infinity of something like 7n plus 3 over, I don't know, n plus 8 to the second power. Well, we look at what the degree of the numerator is. It's a degree of 1 for n, and the degree of the denominator is a degree of 2. And so this is one that we would compare to the series 1 over n. Right? You always sort of just take that, if it's n over n squared, you probably want to compare it to 1 over n. If it's n over n cubed, you're going to want to compare it to 1 over n squared. That kind of thing. So that's sort of the series you want to compare it to. And I feel like this one's pretty straightforward. If you just, if you look at 7n plus 3 over n plus 8 squared over 1 over n, you're just going to end up with a finite number. You're going to end up with that n is going to go up into the numerator up here. You're going to get 7n squared plus 3n. So you have 7n squared over n squared, which becomes 7, which is between 0 and infinity. So you know that they both diverge since this one diverges because it's a harmonic series or because of the series. Did it make sense there? Everyone okay with that? The basic idea there? And then it says that also this limit comparison test says that if we look at the limit as n approaches infinity of a sub n over b sub n and it equals 0, then we know that if b sub n converges, then looks horrible. Then sub n also converges. And sort of on the flip side of that, the limit as n approaches infinity of a sub n over b sub n equals infinity. And we know that if b sub n diverges, then a sub n also diverges. And we can sort of think about that. If b sub n is a convergent series, yet we're still getting a limit of 0, that means that b sub n is increasing more rapidly than a sub n is, and so therefore we must be going towards 0. And therefore, if this one, this one is bigger than this one, so if this one converges, this one must also converge. And so the flip of that is true, that we're going towards infinity, so a must be bigger than b, but b diverges. So if a is bigger than b and b diverges, then a must also diverge. Does that make sense? Any questions there on that? Oh, somebody said something in the chat that I missed. Oh, okay. Nick just said good. Good. Any other questions there on the limit comparison test? All right, and then we also added in the, sort of at the end, we added in the nth root test, which is a good one. So the nth root test is, once again, we need to have a series that has positive terms, just like all these other ones. And if we remember, of course, you can always take the absolute value of the series, because when you find the convergence or divergence of that, if it converges, you know that if the absolute value converges, then the series itself converges, right? So this one is, similar to the thing that we get with the ratio test. It says that we can look at the limit as n approaches infinity of the nth root of a sub n, which I'm putting an absolute value just in case we didn't have all positive terms for a sub n, which is also the same as the absolute value of a sub n to the 1 over n power. Sometimes it's more helpful to look at it like that. And we find that limit, whatever that limit is, if L is less than 1, it converges. If L is greater than 1, it diverges. And if L equals 1, then just like with the ratio test, it's inconclusive. And so oftentimes you might end up with some sort of series that's just being raised, where the whole thing is being raised to the power of n. And if it's all being raised to the power of n, well, then the nth root test is the way to go, because you're going to look at the nth root of it. You're going to take the power of 1 over n, which will cancel out with that power of n, and it's going to make it a lot easier, a lot simpler to evaluate that limit and give you a lot easier expression to look at. So that's the nth root test. Does that one sound familiar? Everyone good with that? Cool. And I'm trying to think if there's any other tests. We did nth root, we did ratio, we did direct comparison, we did limit comparison. We did the nth term test for divergence. We did the p-series and the integral test. So pretty much, yeah. Easiest one, the alternating series test. That's the easiest one. Skipped over that one. The alternating series test. So, I don't think we did this one. An alternating series will converge. So, easy to tell if it converges if 3 criteria are met. So, if the series 1 alternates, that's 1. And obviously, it needs to alternate since it's the alternating series test. 2, if the terms decrease in absolute value. So if you're taking the absolute value of each term and they are getting smaller, right, then that's the second criteria. And our third criteria is that the limit as n approaches infinity of the nth term equals 0. And so if all 3 of those criteria are met, then it converges. And we've seen that one lots of times. We probably looked at the alternating harmonic series when we did this, and it meets all of those criteria. It alternates, it being the alternating harmonic series. The terms decrease in absolute value, 1 to negative a half to positive a third to negative a fourth to positive a fifth to negative a sixth. Those are, take the absolute value, they're decreasing. And as you go towards infinity, it's going towards 0. And so therefore that alternating harmonic series must converge. And that's the alternating series test for convergence. And trying to think, I think that's all of them. So the important thing that you want to remember is anytime it asks you on the AP test, and specifically, they're going to ask you, almost certainly they're going to ask you in the free response on on probably question number 6, a non-calculator free response question, because that's where it always sits. They're going to ask you to determine the convergence of some sort of power series. And they may or may not indicate a specific test to use, but if they don't, you're probably going to want to use the ratio test. That's usually the best place to start. You'll use your ratio test, you'll get your interval of convergence and your radius of convergence and all that fun stuff. and then you will check the endpoints. And as you're checking the endpoints, that's when you're going to use things like, the alternating series test or the p-series test. All these other tests to check those endpoints, because when you check the endpoints, you're plugging in the X value and you're getting rid of all the X's within it. And so and you can use other tests as well, but generally the p-series or alternating series test are ones that pop up pretty often. Or it might look like a geometric series, and so you know whether it converges by just looking at what the R value is. And I believe that is pretty much everything we talked about with series. Anybody have any questions on any of the series stuff or anything else in general that you'd like me to just sort of touch on again?